equations just written as vectors, and in terms of what we call vector valued functions. Okay, so we've already talked about parametric equations, and I just wanted to review a couple things before we get started. We talked about how the slope of a curve, even if x and y are both expressed parametrically, the slope of the curve is still dy dx, but that does mean that we have to write it as dy dt over dx dt, where dx dt is not equal to 0, and that's how we find the slope of a curve at the point. Okay, and then we talked about this yesterday as well, in which the second derivative is given by the derivative of dy dx with respect to x. So by splitting up the numerator and denominator, the dy dx dt over dx dt. So this is the way we talk. This is what we talked about yesterday. We can also consider the derivative as the slope of the tangent line to the curve C, or the slope of the path of the particle traveling along curve C, or as the rate of change of y with respect to x. So this should be nothing new, and the second derivative is the rate of change of the slope of the curve with respect to x. So the rate at which the slope of the curve is changing. Okay. And then a couple other things to keep in mind, that we want to remember that dx dt is the rate at which the x-coordinate is changing with respect to t, okay? Or if you want to look at it as velocity, the rate at which the velocity is changing in the horizontal direction, okay? Likewise, the dy dt is the rate at which the y-coordinate is changing with respect to t, or in which the velocity is changing in the vertical direction. So what's going on with dy dt will tell us if the particle is moving up or down. The dx dt will tell us whether the particle is moving left or right. And keep in mind, we're talking about motion in the xy plane. We're no longer talking about linear motion necessarily. We're talking about, this is the old stuff, okay? We're talking about the new stuff is the coolest stuff, where you can have like a bug, like I said, like a bug crawling around your paper. That's motion in the xy plane, in which both x and y are changing, okay? Linear motion is when you have, I should put new since I wrote the word old. Linear motion is when we have the change, the rate at which something is changing, but only in one direction, okay, left and right or up and down, okay? So anyway, some of the things that I want you to make sure you understand here is that we can define our position as a vector. So we're going to organize our parametric equations, and we're going to define our position as, I shouldn't write it as an x, I should write it as an s, sorry. So the position, velocity, and acceleration will express as vectors. So when our x and y are given parametrically, we would write our position, okay, vector as the x position, or the x position at t, as the x component of the vector, followed by the y component of the vector. So the position of the particle in terms of the y direction. Okay, this is called the position vector. Position. Hope you're writing this down. Position vector at time t. Okay, so likewise we could use, and again, this is when x and y are given parametrically. we can express the velocity at any certain time as the derivative of the x, comma, the derivative of the y as our components of our vector. And those components of our vector, if you want to find the derivative, the velocity at time t as a vector, you would differentiate x with respect to t, comma, differentiate y with respect to t. So you differentiate the respective components to get the velocity vector once you know the position vector. This is called the velocity vector at time t. Okay, and finally we have the acceleration as a vector. Okay, so that's the second derivative of x, and the second derivative of y is the acceleration vector. So we're going to do a couple examples at time t. Okay, we're going to do a couple examples of how we, using this notation here. And one other thing I guess I should point out is that let's do this in the lower left-hand corner here. Make sure you have all the notation in your notes. You should remember that when we differentiate, when we want to find the speed of a particle, we want to find the speed of the particle as the magnitude of the velocity. Okay, the magnitude of the velocity. And if we want to find the magnitude of a velocity, we would take the square root of x prime squared plus y prime squared. And that's the speed of the particle at time t, or the length of the velocity vector. Length of the velocity vector. Okay. And then finally, if you remember, how do we find the distance traveled? Let's go to the length of the arc of the curve from A to B. So the length of the curve, or the arc, on the interval from A to B is given, so we did this in in our most recent lesson. That would be from A to B of the square root of x prime again squared plus y prime squared. So these are formulas that you could memorize these formulas, or you can remember how to generate the formulas. Notice here the length of the curve is dependent upon the x prime and the y prime, but if you remember that the integral from A to B of this would be considered the absolute value of the velocity. Remember, absolute value of the velocity is the speed, and when you integrate the speed from A to B, you also get the distance traveled on the interval from A to B. So the cool thing is that it's all related. So when we want to find just the length of a curve, length of the arc from A to B, if we're not talking about position, velocity, and acceleration, this is the formula we used, but when we are talking about distance, position, velocity, and acceleration, we want to know, the distance is the absolute value of the velocity on the interval from A to B. So absolute value of velocity is here, and anyway, we're going to get into using these formulas, and you would be wise to make sure you understand what these formulas are, and so you have them ready when you need to use them. So let's look at our first example. Already 8 minutes just talking. Okay, let's try our first example, if we can get that in our first video, and then we can transition to the next video and do the other two examples. So example 1, we've got a particle moving in XY plane. Position is given by the two parametric equations, and so we could write the position as a vector, okay? And that would just be the x of t, comma, y of t, which we see what the x of t is. That's t cubed plus 4t squared, comma, t to the fourth minus t cubed. That's our position vector, and here's our two parametric equations that give us our position. So what do we want to find? We want to find the velocity vector when t is 1. Well, the velocity vector is the vector in which we take the derivative of the x component of the position vector, and we combine with that the y component of the position vector, the derivative of the y component. And so the velocity vector is the derivative of our x component here, and that would be 3t squared plus 8t, comma, the derivative of t to the fourth minus t cubed would be 4t cubed minus 3t squared. So that's our velocity vector at time t, but what we want to find is our velocity at time 1. So therefore, the velocity at time 1 would be replacing t with 1. So you replace t with 1 for the x component and the y component, and we have our velocity vector at time 1. Okay, well, when we replace t with 1, we get 3 times 1 squared. So 3 plus 8, so we get 11. And the velocity, the y component of the velocity vector at time 1 would be 1 in place of the t here. 4 times 1 cubed, so 4 minus 3 is 1. So there's our velocity vector at time t equals 1. That's it. So I know there's a lot of talking here. So to summarize, we have our position vector. Our velocity vector is the derivative of each component of the position. And then when we replace t with 1, we have our velocity vector at time 1. Okay? And the acceleration vector when time t equals 2 would be, the acceleration vector, let's go right to that, would be the second derivative of x with respect to t, followed by the second derivative of y with respect to t. Okay? Well, we see the first derivative here is 3t squared plus 8t. So the derivative of this guy would be the derivative of 3t squared is 6t plus the derivative of 8t, which is 8. The derivative of 4t cubed is 12t squared minus the derivative of 3t squared, which is 6t. Okay, so that's the acceleration vector. But we want the acceleration vector when at time t equals 2. And so we replace t with 2, and we get 6 times 2 is 12 plus 8 is 20. Replacing t with 2 for the y component, we get 2 squared is 4. 4 times 12 is 48, minus 6 times 2. 48 minus 12 is 36. And we have our